I have an apple in my hand. What is the value of 1 lu, will you say, or something like that? How wrong are you? Well, this apple has stored energy in it, and not a small amount, as Einstein tells us. We can calculate the energy with the formula E equals mass times the speed of light squared. Let's substitute the values. The mass of the apple is about 200 grams, and the speed of light is 300,000 kilometers per second. How much do we get? Well, we get an energy of millions of billions of joules. What is the monetary value of this energy? We can easily calculate it if we look at the electricity bill. In Romania, for example, each kWh of energy costs around 50 bani. Let's do the calculation again. We find that the value of the energy stored in this apple is about €500 million. I'm rich, Anton, we've gotten rich. I just need to extract this energy. But how? Well, here's the trick. Today, no one can extract the energy from this apple because it's made of stable atoms. However, a century ago, physicists discovered something special. If the apple were made of uranium atoms, then they could release a percentage of the energy stored in them. Let me calculate. 1% of €500 million means €5 million. That's still something. How can I do that? Let's see. First of all, I need an amount of uranium as big as the apple. Where can I find it in the mines in Romania? Of course, in the extracted soil, there are all kinds of ores that need to be separated. After extraction, they will be left with several forms of uranium atoms, called isotopes. Let's remember that an atom is made up of a nucleus around which electrons orbit. The nucleus itself is made up of protons and neutrons. What distinguishes isotopes? Well, the nuclei of uranium isotopes have the same number of protons but a different number of neutrons. What we want is uranium-235, meaning that uranium which has exactly 143 neutrons and not any other uranium. Normally, after separating the ores, we are left with 99% uranium-238 isotope and only 1% uranium-235 isotope. So we get to work and remove the first form of uranium that we don't need. The process by which we separate uranium-235 from the other forms of uranium isotope is called enrichment. Let's say now that the apple is made only of uranium-235. I wouldn't want that. Why? Well, I'd have an unpleasant surprise. The uranium apple would emit a huge amount of radiation that would kill me in a very short time, probably even in minutes. That's the reason why some of the firefighters who arrived at the Chernobyl nuclear power plant after the explosion died. The firefighters came to put out the fire. Without realizing it, they started touching objects around them, especially graphite rods, which were contaminated with uranium. Out of the few dozen firefighters and operators, 30 died in the first 3 months, and others later from cancer. How incompetent could the plant managers have been to call in the firefighters without warning them how dangerous it was, without protecting them? It's a theme that the film Chernobyl highlights very well. Some of the causes of the accident were incompetence and lack of experience. Let's get back to Marumeu. If it's made of uranium, 235 is radioactive. Bad. I need to protect myself. That's why I put it in this protective virtual container. What does it mean that uranium-235 is radioactive? Well, if I put detectors around, I see that the uranium apple emits a bunch of alpha particles at very high speeds. Alpha particles are the bullets the investigator in the Chernobyl movie was referring to. Their speed is close to the speed of light and they have very high energy. Where did they come from? For this, we need to put a microscope on the uranium apple. We look at a millimeter on its surface. We divide the millimeter into 1,000 pieces. Now we have a micrometer. It's the smallest thing you can see with an optical microscope. Then we take that micrometer and divide it into 1,000 more pieces. Now we have a uranium atom. We enlarge it. What do we see in the classical model? Some electrons orbiting around a very small nucleus. The nucleus is made up of two types of particles: protons, which have a positive electric charge, and neutrons, which have no electric charge. The thing is curious, like charges repel each other, that's what we learned in school. So how do protons stay together, since they have the same type of electric charge and repel each other? The answer lies in a new force of nature, called the nuclear force, which acts at short distances. So, when protons get close to each other, this new nuclear force comes into play, which makes them attract each other at least as much. Alone, the nuclear force between protons isn't sufficient. This is where the crucial role of neutrons comes in, as they are also subject to nuclear forces. Neutrons act like a very effective glue between protons, pulling sometimes on one, sometimes on the other, in such a way that they don't let them drift apart, even if that's what they would want. That's why there's an interesting law in nature. In stable nuclei, the number of neutrons is approximately equal to the number of protons. If there were fewer neutrons, they wouldn't be able to hold the protons together. If there were too many neutrons, the balance would also be disrupted and the nucleus would break apart. Moreover, the more protons an atom's nucleus has, the more fragile the balance becomes. That's why very heavy atoms don't exist stably in nature. They are created only in laboratories. Let's go back to our apple made of uranium-235. The nucleus of uranium atoms is large, having 92 protons and 143 neutrons. Because of this, the nucleus is quite unstable. The neutrons barely manage to keep the protons together. From time to time, a nucleus in the apple can no longer withstand the electric repulsive forces between the protons. Then, the nucleus splits into two pieces, a process that continues further. In the end, the alpha particle is released, all of them shooting out at speeds close to the speed of light. These particles carry some of the energy of the atom originally from uranium. I need this energy if I want to win the 5 million euros stored in the energy of this apple. What can I do? Well, I can place the apple in a glass of water. Then the alpha particles come out, then they hit the water in the glass like bullets, giving energy to the molecules there and thus heating the water. When the water heats up, it boils, so I place a propeller on top and add an electric generator. I've created a turbine. When the turbine spins, it gives me electricity, which I then sell and thus earn those few million euros. Alright, you realize this is an oversimplified scheme, but it highlights the essence. Thus, I make use of the spontaneous disintegration of uranium atoms and extract the kinetic energy of the reaction products scattered after the nucleus disintegrates. I can do that, but I have a problem. Not all uranium atoms disintegrate spontaneously, only a few do. In fact, if I wait a year, only one atom out of 1 billion will disintegrate spontaneously. That's why, for the whole apple of uranium to disintegrate, I would have to wait about 1 billion years. Where would I get that much time? Anton, any idea what I can do? You're asking me? I just started my vacation. Okay, here's how it is. The uranium nucleus is full of protons that want to repel each other. The nucleus is held in a fragile balance by neutrons, like a house of cards. If we throw a walnut at a house of cards, it will collapse. The same thing will happen to the uranium atom's nucleus if it is bombarded with a particle. The particle will destroy the fragile balance of the nucleus and it will disintegrate. But which particle should you use to bombard it? I could try, for example, with other protons, but protons are positively charged and will be repelled by the existing nucleus because it is also positively charged. It's better to use neutrons, which, being electrically neutral, can pass through the electric potential barrier of the nucleus. But there's a trick here too. Watch the accompanying video, where I played with neodymium magnets. You see how the small magnet is attracted to the large magnet. The small magnet partially enters an orbit, then falls onto the large magnet. What happens if I throw the small magnet hard? let's do the experiment. We can see that this time, even though the small magnet passes by the big magnet at the same distance, it is no longer captured. Why? Because it has too much speed and the attractive force doesn't have time to take effect. The same thing happens with neutrons when we bombard uranium nuclei with them. If the neutron's speed is high, they pass by the nuclei. If the neutron's speed is low, then they have time to come under the influence of the nuclear attractive force. The neutrons are deflected in their movement by the nucleus, reach it, and break the fragile balance of protons and neutrons. From there, the nucleus breaks into various pieces, releasing other neutrons in the process, but also the energy we need. This was demonstrated by the German physicist Otto Hahn in 1938 German. The years of World War II, the atomic bomb, clearly topics for the future. Otto Hahn showed experimentally that this is the case. A slowed down neutron is capable of initiating the disintegration of the uranium atom. Don't forget, let's get back to our uranium apple now. How can I disintegrate all the uranium atoms in the apple without waiting a billion years? Well, I bombard it with slowed down neutrons, one for each atom. But I need a lot of neutrons, because there are a lot of atoms. What can I do? Let's remember that after disintegration, uranium emits all kinds of particles, like alpha particles, but it also emits neutrons. I could bombard the uranium atom with a single neutron, thus disintegrating the first atom, which in turn emits 3 neutrons. In the end, those 3 neutrons will each bombard 3 uranium atoms, and after disintegration, they will generate a total of 9 neutrons, and so on. This way, I create a chain reaction. In practice, I only need a single slowed down neutron at the beginning to initiate this chain reaction. I have only one problem. As a result of the disintegration, the neutrons that come out of the nucleus shoot out at speeds close to the speed of light. I have to slow them down before they bombard the next uranium atoms. I need a slowing medium. That's why around the core I can add graphite rods. Their role is to slow down the neutrons that are moving at high speeds. This way, I've come close to the design of a nuclear power plant like the one at Chernobyl, the design we see here. Here we recognize the uranium rods, which are the equivalent of my core. Then we see how the uranium rods are placed in water, the equivalent of my glass of water. The neutrons and other particles that come out of the uranium atoms after they split will heat the water, which will start to boil, setting the turbine in motion. In addition, you can also see some graphite rods here. Their role is to slow down some of the neutrons. Because the neutrons are slowed down, they will split the uranium nuclei they encounter along the way. By sustaining the chain reaction, the graphite rods act as a neutron moderator for the reactor. This nuclear reactor has a problem. If I hit it with a single slowed neutron, I will initiate the chain reaction and the reactor will go to maximum power. How do I stop it? For that, you can see in the figure some additional BOR rods. Once inserted, these BOR rods block the neutrons from moving from one side to the other, thus preventing the chain reaction. Simply put, if I insert the BOR rods, the reactor will operate at a lower power and it can even be shut down. If I remove them, the reactor will operate at maximum power. And that's how we got to. If you like the reaction, don't forget to subscribe. I hope so. Thank you for watching. Goodbye. We stop at this design, and so we've reached the long-awaited question: what went wrong at Chernobyl? I'll start by saying I watched and liked the Chernobyl series. The first 4 episodes are action-packed Hollywood style. I waited for the final episode, which had less action and focused on explaining physics. That's why I won't tell you who did what. In fact, I won't go into the advanced technical details either, which are explained in the last episode. I just want to explain to you the main mistake, which is related to physics. If you're sensitive to movie spoilers, stop here and watch the movie now. With the physics I've explained to you, you'll definitely figure it out too. Otherwise, if you don't mind a little spoiler, we can move on. Anyway, what I'm telling you here is just a small part of the whole complex system explained in the last episode. In other words, even if you find out the big mistake from me, you'll still enjoy the details added in the last episode. So, what happened? The Chernobyl reactor went through some tests in the days leading up to the explosion. It operated for a long time at low power. Basically, the BOR rods were lowered and the nuclear chain reaction was inhibited. However, this had a drawback known only to a few of the technicians there. Thus, as a result of the nuclear reaction, the uranium atom disintegrates into smaller atoms. One of these is the xenon atom. It has a disadvantage. The xenon atom blocks some of the neutrons, acting as an inhibitor for the chain reaction. Normally, that's not a problem. At normal reactor power levels, the temperature is high and the xenon atoms break down further. In the days before the accident, however, the reactor was operating at low power, with the BOR rods inserted into the reactor. That's why the xenon wasn't burned, meaning it didn't break down further. It acted as an additional inhibitor alongside the BOR rods. On the fatal night, when the technicians wanted to increase the reactor's power, they ordered the BOR rods to be removed from the reactor. Normally, the power should have increased because the nuclear reaction was no longer inhibited. Surprisingly, however, the power did not increase significantly because there was xenon in the reactor. The technicians withdrew more BOR rods, but the power still didn't increase. At one point, they removed all of them, and still the power remained low, a sign that the nuclear reaction was inhibited. This is the critical moment. The situation isn't normal. With the BOR rods withdrawn, the reactor should have been running at full power, and the uranium should have been burning very efficiently. Instead, the uranium wasn't burning because it was being inhibited by the xenon atoms. Alright, you might ask, but why did it explode if the chain reaction was being blocked by the xenon atoms? The simple answer is that the xenon was not under control. What caused the explosion was a brief moment of nuclear reactions being activated. For that, a small catalyst for the reaction was needed, coming from somewhere else. However, once the activation started, the reaction could no longer be stopped. As the temperature rose, the xenon burned up quickly. From that moment on, there was nothing left to stop the reaction. It was accelerating explosively because the control rods were raised. In a few seconds, the nuclear reactions of the uranium atoms overheated the small amount of water present there and evaporated all of it. And you know what happens with the water that evaporates in the pot on the stove? It creates pressure. The same thing happened in the out-of-control reactor. The huge pressure broke through the walls of the chamber and the entire core of the reactor exploded. In a few moments, the graphite rods were contaminated with people. While we clean, we take an activation type. So during the activation time, we clean, we take another activation type. So while we clean, we take another type. The series' first episode. Okay, you might ask, but what was the catalyst? What started it? The reaction at the beginning when there was xenon in the reactor? I'm not going to tell you the answer. It was a surprise for me too. I'll let you discover it yourselves in the last episode. It's enough to say that it was a design flaw in all reactors, of the same type as the one at Chernobyl, a problem that was later corrected in all reactors. Enjoy watching? Alexander Alexanderson asks me this: I know a physicist who says it's possible to travel in the multiverse. Who should I believe? It's okay, Alexander. There are two types of multiverses: spatially connected multiverses and multiverses that are not connected spatially or temporally. In the second case, you can't travel from one to another. The first case is more interesting, and I'll give an example. Even with our own universe, well, at the edge of our universe, somewhere very far from us, space is accelerating at a speed that right now has surpassed the speed of light. Because of this, everything that is there is lost to us forever. What does that mean? It means that if a signal leaves from there and wants to reach us, it can't get here, because space there is receding at a speed greater than the speed of light. And vice versa, if I send a signal there, again my signal won't reach there, because that space is receding at a speed greater than the speed of light, and the speed of the signal can't exceed the speed of light. Because of this, the two regions of space are causally separated. We say that we can call them, if you want, very simply multiverses. This is a case where these multiverses share the same space, but they are separated and you can't travel from one to the other. That's what happens, for example, in the theory of inflation. Okay, it goes like this. No, I had speed.
Means that the universe, it is already traveling.
Part.
Our universe is traveling at a speed faster than light.
So the far side of our universe. So the space it's in is expanding at a speed faster than the speed of light. So it's moving away from us at a speed faster than the speed of light. From us, yes.
So yes, so relatively speaking, I say yes. Did you give it for traveling at a speed faster than the speed?
Yes. Compared to them, yes. Compared to them, yes. But did you ever have a problem?
Well, that means I've already traveled at a speed faster than the speed of light.
Yes, because we're in space. You know, because Einstein's theory says this. The speed of light cannot be exceeded in a local frame of reference. What does that mean? It means that if you're standing in one place, you can't see an object moving relative to you at a speed greater than the speed of light. But us and the object, together with everything around us. In the space we're in, we can move at a speed greater than the speed of light if we take the space with us. Just like a ship takes its passengers, yes, just like the passengers. Just like the passengers. Just like the passengers.